Alright everyone, welcome back to the AI Research Roundup. I'm your host, Alex, and today is May 3rd, 2025. We're diving into a really interesting ICLR conference paper published just over 3 months ago, back on January 22nd, titled Spread Preference Annotation. So this paper tackles the high cost of aligning LLMs with human preferences by introducing a framework, SPA, that does this efficiently, using very little human annotated data. Okay, so looking at the diagram here, it clearly illustrates this SPA framework. You can see the two main stages. First, generating new preference data. The current LLM creates responses, and preferences are judged against a reference model using those logits we talked about. Then, there's the preference learning phase, which crucially includes self-refinement to handle noisy labels. It's this iterative loop that progressively improves the model. Building on that iterative process, this figure clearly shows the performance improvements over time. It's plotting the length-controlled win rate against GPT-4. Across the different refinement stages, notice how the blue line, that's SPA, consistently climbs higher than the iterative DPO baselines, using either pair RM or an LLM as judge. This really demonstrates the effectiveness of SPA's self-refinement loop in boosting alignment, compared to other iterative approaches. Moving to the results, this table then details the main evaluations on Alpaca Evolve 2.0 and MTBench. So look at the SPA row. Using just 3.3% of the gold labels, it achieves a significantly higher length-controlled win rate, 15.39%, and win rate against GPT-4, 21.13%. That's way better than standard DPO on the same data, and even beats Zephyr, which used 100% of the labels. Really impressive efficiency. Okay, now this table specifically zooms in on the preference judgment aspect. It compares SPA directly against iterative DPO methods, one using an external reward model, pair RM, and another using an LLM as the judge. And look, SPA clearly wins out on Alpaca Evolve 2.0. achieving much higher win rates without needing an external model. MTBench scores are closer, but SPA remains very competitive, showing the strength of its internal preference judgment mechanism. Okay, so this next table really hammers home the data efficiency point. It compares SPA against standard DPO, but this time, it varies the amount of initial seed data used, from just 0.8% up to 10% of the ground truth labels. And across the board, whether you look at length-controlled win rate or standard win rate, SPA consistently outperforms DPO, often by a large margin. It really shows how well SPA leverages that small initial dataset. Okay, building on that data efficiency, this table demonstrates SPA's compatibility across different models like Phi2, LLMA3, and Phi3. You can see that in each case, SPA, using just 3.3% of the gold labels, achieves notably better Alpaca Evolve 2.0 win rates than both standard DPO on the same data and the base SFT model. It really underlines the broad applicability and robustness of the SPA framework itself across various architectures. Alright, this last table is an ablation study. It really digs into why SPA is effective by testing different combinations of its key components. You see the columns for data expansion, self-refinement, and decoupled noise detection. Adding each one incrementally boosts the Alpaca Evolve 2.0 win rates. The full SPA configuration, with all three enabled, gets the best scores, clearly showing that both self-refinement and the decoupled noise detection significantly contribute to the final performance. So wrapping things up, what we've really seen today is that C provides a very practical and efficient way to align LLMs. The big takeaway is achieving strong performance, beating even models trained on full datasets, using just a tiny amount of human preference data, thanks to its clever iterative refinement and direct logit-based preference judgment. Well, that's our look at SPA. Thanks for joining the AI Research Roundup.